Hi, I'm Ali Safavi. I'm a graduate student at Kettering University, Flint, Michigan, and I'm really sorry that I couldn't be there. I had some problems of coming to Germany. Today I'm going to talk about my paper, which is a novel MPC approach to optimize force feedback for physical human-robot interaction. Active constraints or visual fixtures are modern control algorithms that assist humans with robot interactions. They regulate the motion of the users by guiding or assisting them through the task. Many control algorithms have been already proposed for haptic guidance, but one of the weaknesses of the common optimal and adaptive controlling approaches that have been suggested is that they require state space models, which not all these commercial haptic interfaces do provide them. Another problem with these systems is that most of them propose linear solutions for a complicated control problem. So in our case, we have a human in the system. Yeah, we are proposing a new framework which is based on model predictive control. The model predictive control predicts the system, which is used in many processes outside of the human-robot interaction, and based on this prediction, it gives the best solution, which I'm going to talk more about it. I'm just giving a general idea about which kind of control we're going for here. So, in our case, we use neural networks to model a robot, and then we use genetic algorithms to optimize the movement. But as this optimization process takes a long time, we have used neural networks again to somehow create a lookup table for a specific virtual environment. Here we have a prototypical controlling task where a predefined model generates desired motion and desired behavior that we want from the user, and the controller regulates the motion based on those referral points. We perform a desired set of motion and use hidden Markov models to model those set of motions. In this work, we do not focus on how to model the motion and the task, but rather than how to use this model to optimize the human-robot interaction and have a more sophisticated control approach. We have a task model which generates the desired motion, which includes velocity and position, direction of the movement. Compare that to the difference between that motion and the user's motion. Optimize the solution based on the model that we have of the robot. So to get into the framework, let's first talk about MPCs. MPCs, model predictive control or receding horizon control, which an online optimization of a finite horizon optimal control problem for each instant is solved. The current state of the system is considered as the initial state, and the optimization yields an optimal control sequence of future control actions to regulate the error. However, the system only uses the first of the sequence which was calculated and applies it to the system. And some advantage of this control strategy is that its multivariate optimal solution and its ability to handle constraints and its predictive nature. The concept of this approach doesn't really rely on a specific modeling or optimization algorithm, which MPC has proven effective in many applications similar to robot-human interactions and in robotics, and especially in different control applications. But the main drawback that these controllers have is that the user is slower than common control techniques, which is because of their heavy computational load. There is a concept of fast MPCs, which have been suggested in different ways, but first step is that we need a reliable model of the robot, which for that, a rich dataset is needed of the different dynamics of the robot, where we have to provoke and capture the different dynamics of the robot, of how the velocity and the acceleration of users changes based on the forces that the robot puts on their hand. So the robot here has been considered as a black box. Using this, we consider velocity and acceleration of the end effector in the VE. We extract it from the position of the robot in each instant, and the generated robot force as input of the black box model, and then the resulting velocity as the output of the black box model. To simplify the study, we have only considered the x and y axes of the Cartesian coordinate system. We collected the velocity and the acceleration of 20 users who had interacted with that virtual environment and using that haptic interface, alongside with the force that was applied to their hand and the resultant displacement of the movement that they had. We used a multi-layer perceptron of 2 hidden layers and 20 neurons per layer to model this, and you could see that the results show that this model is acceptable. So this regression plot shows a regression between the empirical data and the simulated data generated by the model. This includes a set of training data, test data, validation data, and an overall regression in which all of the data set has been included. These results show that the precision of the model in capturing the behavior of the robot is good. By developing the model of the robot, next step is to optimize the force. As I said before, we use genetic algorithms. In these algorithms, and based on natural selection process and genetic recombination, a random initial population of solutions are used and defined, and the algorithm evolves them over a number of generations towards an optimal solution. This method could be used for both constrained and unconstrained problems and could be applied to the problems that are not suited for standard optimization problems. We use k-means clustering for vector quantization to use it for the hidden Markov model that we have considered for the task model. 7 participants were asked to follow the set of motions we use but with visual guide that we had defined from before. For each instance and location of the virtual environment, the closest point of the reference motion was calculated. The desired direction of the motion was defined as the direction of the reference sequence moving from the closest cluster towards the next cluster of the motion sequence. The goal of the control was to force the subject to finish the task faster by providing force in the direction of the sequence. In order to optimize the generated force, the task model would generate an estimation of the direction of the movement for a small window ahead. The optimizer finds a sequence of optimum forces and applies the first one to the current instance. An optimum force value has been calculated for each data sample from the collected data and the motion reference. We have reasonably considered different variations of a user movement for completing the desired task. We use a neural network and a multi-layer perceptron, to be more precise, to map the inputs into the optimum force vector as a lookup table concept. The model is similar to the model that we used before. This overall approach could be easily extended for different multi-model interactions. Based on the task model and the considered performance metrics, the offline optimized phase of this approach provides flexibility for coping with complex motions and feedbacks. Furthermore, by adding different variables to the output of the optimization procedure, different forms of feedback could be provided in an optimized form. However, such an approach requires further considerations which are out of the scope of this. We use the setup that you could see in the picture to evaluate this method. For evaluating proposed control approach, we have compared it to 3 spring impedance controllers holding different values for the gain. Such controllers are most common constraint information method applied in the literature, where the applied force is a linear function of the error between the desired and current points. The control mode consists of 1. When no force is applied, so only visual guidance. 2. A spring impedance controller using a relatively large gain. 3. Spring impedance control with a relatively medium gain. And 4. A spring impedance control with a relatively small gain. And 5. Our MPC approach. As mentioned before, we have considered 3 metrics for performance. 1 is task completion time. 2 is motion smoothness. And 3 is average speed. 4 subjects carried out the task with 5 repetitions for each control mode. A witting subject design was used for the study to decrease the learning effects of interacting with the robot. For each repetition, the method of providing force was randomly chosen. In order to provide a smoother force and to protect the haptic device, a filter was applied to limit the changes in force in each direction to 10% of the last instance. This figure shows a sample repetition for different modes of control. As shown in the figure, for the impedance controllers, as the value of the gain increases, the motion experience has more ripples. This is a result of large values of change in the provided force. When the user moves through the task, the reference point constantly changes, and as a result, the force value is rapidly varying. Since the gain value of the controller directly affects the value of the provided force, large gain has resulted in decreased smoothness of the motion compared to the other approaches. The MPC approach shows a relatively smooth motion, a result of an optimum balance of time and motion. This figure shows the MPC approach has the least average for task time completion. As expected, when no force is applied, the subjects take more time to complete the task. For spring impedance controllers, the medium gain seems to have a better performance compared to the others. For the large gain values, there is a higher task completion time. This could be due to the large sudden changes in the value of the rendered force feedback. However, for the smaller gains, the small average force feedback has resulted in users taking more time to complete the task. Overall, it seems that an optimal value for the gain is leaning more towards the median value, whereas the MPC has the best results in this criteria, improving the performance of the participants. This figure demonstrates the results for the average speed, which is directly related to the task completion time. Higher completion times have resulted in smaller average speeds. As seen in the figure, the MPC approach has resulted in the highest average speed. The results for motion smoothness are presented in this figure. Among more effective force feedbacks, the MPC shows more promising results. The results show a trade-off between speed and smoothness. In the absence of force, best motion smoothness has been achieved. When force is applied, motion smoothness is decreased for larger gains. For the smaller gain values, the amount of force is too small to significantly affect the motion smoothness. These results could also be interpreted from the first figure. The overall results of the evaluations validate MPC as a promising control strategy for controlling robot manipulators and to increase users' performance compared to classical and common control methods. Furthermore, the results suggest providing force feedback in general could improve user performance in criteria such as time, and also by advancing the force rendering techniques, a balanced time-motion performance could be delivered. A novel combination of MPC and neural network was presented for human-robot shared control. In order to develop the proposed approach, a general MLP network model of the robot was developed and validated. The MPC framework optimizes the output force based on the reference task model using genetic algorithms, and the control goal is to encourage the users to increase their time-related performance. The proposed MPC has been compared to free spring impedance controllers. The results demonstrate that the MPC approach managed to increase the performance of the subjects in completing a task in terms of time-related metrics with a better smoothness trade-off compared to the classical impedance controllers. For future work, I suggest faster optimization techniques, and it could be investigated into seeing if real-time optimization could actually be achieved. Furthermore, we could personalize the physical human-robot interaction and see if that would improve the learning experience of the users and the interaction that they have with the robot. Furthermore, this approach could be applied to the training of skill-based practices such as minimal invasive surgery to encourage novice trainees to complete a task similar to the performance of an expert. Thank you.